This is the Pre-AP Geometry, Chapter 10, Part 1 test. Review. First problem. We have several shapes inscribed in a circle. AC is a diameter, which means that triangle ABC is a right triangle because this angle intercepts a semicircle. So we know that 2p plus 3p together equal the other 90 degrees of that triangle. The bottom part of this diagram is a quadrilateral inscribed in a circle, and a quadrilateral inscribed in a circle, opposite angles are supplementary. Make sure you know that for the test. Next problem. You first need to find out the radius of the circle. The radius is going to be the hypotenuse of that triangle. So 4 squared plus 2 squared equals r squared. But for the equation of the circle, which is what we actually want to be substituting in there is r squared. So it's going to be equal to 20, which we get from there. H and K are the coordinates of the center of the circle. Remember, the sign on the coordinates is the exact opposite of what the actual coordinate is. So the center of this circle is 4, 5. It's going to be x minus 4 squared plus y minus 5 squared equals 20. The circumference of this circle is going to be 2 times pi times the radius, which is 2 times pi times 2 squared of 5, which is 4 pi square root of 5 in exact form. 4 additional points that are on circle O. The way that we got to this point originally, or to point P, is you go over 4 down 2. We can easily find more points. We can go left 4 up 2, left 4 down 2, which also means we could go over 2 up 4, either left or right, and over 2 down 4, either left or right. So what we have are now, in addition to point P, 7 other points on that circle. Any of those will do. Now we're doing this without a graph. The equation of the circle hasn't changed. Keep in mind that this equation comes directly from the Pythagorean theorem. X minus h is just the horizontal distance, y minus k is the vertical distance, and r is the diagonal distance. If one of these, either x plus h or y minus k, is 0, then we just have the horizontal or vertical distance. Then the radius is just going to be the horizontal or vertical radius. So we need the center, the radius, and the equation of. We have the 2 points of the diameter. So we need to find the center, which is going to be the midpoint of the diameter. The radius, which is going to be half the length of the diameter. And once we find those, we can write the equation of the circle. So the midpoint is average the x's, average the y's. We have 3, 2 as the center. The length of CD, Or if we want to be pretty confident with ourselves, we could use our center and go just the length of the radius. But just in case I messed something up finding the center, I don't want to mess up the radius as well. So what I'm going to do is I'm just going to actually find the whole length of CD, cut it in half. So the length of CD is going to be the difference between the x coordinates, which from -2 to +8 is 10. The difference between the y coordinates from -4 to +8 is 12. And keep in mind we're taking half of that. One half of q squared is 61 when you simplify that, which means that the radius itself equals 1 squared is 61, which should be what we got if we went from our coordinate of the midpoint of the center of the circle to either C or D. The equation of the circle, as given above, is going to be x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared equals the radius squared. Next problem, finding the center and the radius. Given the equation, the center is going to be the opposite of the x in here and the opposite of the y in there. The radius is going to be the square root of the number on the other side of the equation. Which in this case is 4. For two circles to be concentric or cocentric, they need to have the same centers, which means I don't care what's on this side. All that tells me is how big the circle is. What's here and here tells me where the circle is centered. So if I want them to be the same centered, I need to make sure that that side of the equation is exactly the same. So I would need 9 to equal -h, and I would need 15 to equal -k. Or you could say the center of this circle is 9, -9, -15, so the center of this circle has to be the same thing. So h would have to be -9 for that parenthesis to look like this parenthesis, and this would have to be -15 for this parenthesis to look like that parenthesis. This is just a really fancy way of asking you what is the center of the circle given in the first equation, which we actually did right there. First thing to do here is just put all the information in there. We know AB is the diameter, so this is all 180 degrees. We know that BC is 46, so AC is going to be the rest of that 180 degrees, or 134 degrees. Number 7, very much like number 1, we need to realize that if this triangle is inscribed and this one of the sides of the triangle is a diameter, then it has to be a right triangle. So the other two angles have to add up to the other 90 degrees of that triangle. Hopefully you remember how to add fractions from middle school. 1/2 and 1/3, their common factor is 1/6. So in order to get this to be 6, we need to multiply by 3. In order for this one to be 6, we multiply by 2. So when we're adding our fractions here, we have 3x over 6 plus 2x over 6 plus 5 equals 90. I'm going to subtract the 5 as I do this and get 5/6 x. I'm going to divide by the 5, and I'm going to multiply by the 6. And I get x equals 102. This lovely problem here. We want to know the size of angle ACB. We know that this arc here is a 40-degree arc, and we know that angle ACB has a vertex on the circle, because remember the first question you need to ask yourself is the vertex on, in, or out of the circle? The vertex is on the circle, the angle equals half the arc. Or in this case, 20-degree angle. The size of angle OAB, this angle here, we need to keep in mind that because these two are radii, we have an isosceles triangle. So these angles are the same and add up to 140 degrees. But because they're the same, we're going to split 140 two even ways, so we get 70 and 70 that add up to be 140. So 70 degrees there, and 20 degrees for the first part. Part 3 of this beautiful problem. Already the circle is 5 centimeters. We would like to know the length of this arc right here. What I do know about this arc is this is 40 degrees of the full 360 degrees of the circle. I would like to know how long that is compared to the full circumference of the circle. Which in this case is 10 pi, diameter being 2 radii. First thing I'm going to do, if I can, in my head, is simplify this thing, because this is going to get pretty big if you're doing this in your head. So 10 cancels. I can also cancel out the 4 into 36 and make this fraction 1 over 9. So the equation that I really have to solve is 1 over 9 equals x over 10 pi. Simple matter of multiplying both sides by 10 pi. I get x equals 10 pi over 9 centimeters. To find the sector area, similar process. What I'm being asked for now is how much area does this pie slice take up? It's still 40 degrees of the circle. And I still want to know how big that pie slice is, except now I'm not going to go out of the circumference, I'm going to go out of the area of the circle. I'm going to do the exact same simplifying that I did earlier. That ends up being 1/9. I'm going to multiply both sides of this equation by 25 pi. And I get 25 pi over 9 square centimeters equals the area of the sector. The minor sector, meaning we are going the shortest distance around from A to B. We are not going to go the long way around the circle. A fairly simple problem. I'm going to call this y. Actually, I'm going to call it what it is, which is 102 degrees. That 102 degree angle is in the circle. It makes this arc and it makes this arc, because remember, when you're talking about inside the circle, if it's not in the center, we need to use the double-sided flashlight. So this 102 degree angle equals half of the one arc plus the other arc. Or if you'd rather think about it as the average of the two arcs is the angle that makes it, Great, it means the exact same thing. To solve this equation, first thing I want to do is I want to get rid of this 1/2, so I'll multiply by 2 on both sides of the equation. Subtract 125, and x equals 79 degrees. Next problem. I don't know what this arc is or this arc, but I can tell what the smaller arc is in relationship to the big one. So this arc right here is the full circle, taking away the 102, taking away the 135, and taking away the x, which when you simplify it becomes 123 minus x. Because the angle is outside the circle, the angle equals half of the big arc minus the smaller arc. Again, I'm going to multiply both sides by 2. I have 74 on this side. I'm going to simplify as I go on this side. This negative sign gets distributed through the parentheses. So I actually have x plus x minus 123. And then this problem gets solved just like any other Algebra 1 problem that looks like it. Can we have a square inscribed in a quadrilateral? Yes, that's how we constructed a square, or one of the ways we constructed a square. If it is inscribed inside the quadrilateral, both of the diagonals of the square will have to be diameters because they bisect each other. Will also have to be perpendicular to each other because it is a rhombus. A rhombus itself cannot be inscribed in a square, inscribed in a circle unless it is a square, because the opposite angles need to be supplementary, and normally in a rhombus they are congruent, and the only angles that are congruent and supplementary are 90-degree angles, which is the exact logic we're going to use for the parallelogram. You cannot inscribe just a parallelogram inside of a circle, because in a parallelogram, opposite angles are congruent. If you inscribe a quadrilateral, the angles are not only congruent, but they are also supplementary. And the only angles that are congruent and supplementary are right angles. So if you inscribe a parallelogram inside of a circle, it has to be a rectangle. This one I know gives some people trouble. We're going to do the same thing we did on the problem a couple back, and we're going to find out this angle in terms of x. This is the circle taking away the x part of the circle. Y is 1/2 of the big arc minus the small arc. Turns out you don't actually need those parentheses in there. And we can distribute the 1/2. So there is y in terms of x. Another way we could look at this problem is if we drew the radii to the tangent lines, which will make right angles, this arc, x, is equal to this angle, x. Since we know that angles inside of a quadrilateral have to equal 360 degrees, we can take out the 90 degrees, and we're left with 180 degrees. So the x plus y together have to equal 180 degrees, and then we solve for y, because it says find angle y in terms of x, simplified completely. Either way you want to approach that problem, perfectly good reasoning. Number 13, we're going to employ a similar trick in that we need to find what this arc is in terms of x. So we know it's the full circle. We've lost 100 degrees of the circle, or 100 degrees are accounted for, and then the x. So this arc here is 260 degrees minus x. The angle is outside the circle, so the angle equals 1/2 of the big arc minus the small arc. I see that these numbers inside the parentheses are going to be even. I'm going to keep the 1/2 on this side so I can distribute it later. When you distribute this negative, that becomes 2x minus 260. Take half of the entire parenthesis, and x equals 185 degrees. Number 13, any radius that touches a tangent line is automatically a right angle. We know this because this arc is 180 degrees. Also, if we extend the tangent line, this arc on this side also has to be 180 degrees. And these angles have to be congruent because they make the exact same size arc, and they have to be supplementary because they are a linear pair on this tangent line, and the only angles that are congruent and supplementary are right angles. You will see a similarly somewhat complicated problem on your test. First thing to do, put in all of the givens. I'm going to find all of the inscribed angles I can. I know that angle 2, because that flashlight, so to speak, is pointing at the 40 degrees, must be half of the 40 degrees, or 20 degrees. Because it's the same arc that this angle makes, this angle is also 20 degrees. We can also look at angle 5, which makes this arc when you turn the flashlight on, which means that angle 5 is half of 108, or 54 degrees. Then I'm going to use this triangle that have the 54 and the 20 in it to find out the missing angle, which will be vertical to angle 4. 106 degree angle, 106 degree angle. Just for a second, I'm going to call these y. The vertical angles that make these two are the 106 degree angle. So 106 equals half of, because it's inside the circle, we're going to add the two angles. Half of y plus y is half of 2y, which means y, 1y, equals 106 degree arc. Finding angle 3, we can do that the same way we found angle 5, because they both make arc UZ. So angle 3 is also 54 degrees, or we could have used this triangle to find that as well. Finding measure angle 1, if we shine the flashlight from measure angle 1, it makes a 106 degree arc, which means that it is a 53 degree angle. So I'm just going to fill in what we know. We know angle 1 is 53, angle 2 is 20, angle 3 is 54, angle 4 is 106, angle 5 is 54. I'm to break this shape up into what it is made up of, and that is a rectangle with a semicircle on both ends. We know that the perimeter of the whole shape is 400 meters. Because this is a rectangle, that's also 120, which means that the two semicircular parts of the track need to make up the rest of the 400 meters. Which totals to be 160 meters. The D, I'm going to take out the middle part of the track, the rectangular part of the track. This diameter of that circle, by putting the two ends together, is the distance between the two parallel lines on the track. We just found out that the circumference of this circle equals 160 meters. The circumference, we also know, equals the diameter times pi. So without rounding, circumference of circle is 64 pi. The diameter is 64 because circumference equals the diameter times pi. The radius is half the diameter, and the length of an 80-degree arc, 80 degrees of the full 360 degrees of the circle, equals, and we're talking length now, so we're going to use the circumference, 64 pi. And I don't know what the arc length is yet. What I do know is that I can cross off those tens. And I can also divide by 4. So the equation I'm left with is 2/9 equals x over 64 pi. Cross multiply, you get x equals 128 pi over 9 centimeters. Area of the shaded region. We have a sector. It is a 40-degree sector out of the full 360 degrees. I don't know what the shaded area is, but I do know that the full area of the circle is going to be 64 pi. Wow, this looks remarkably like the previous problem. We're going to simplify these to 1 over 9 again. Cross multiply on both sides. The area of this sector, on number 17, equals 64 pi over 9 square centimeters. For number 9, what we really have is this full pie slice with the triangle cut out of it. So that's how we're going to solve this problem. We're going to find the sector. We're going to subtract the triangle. The sector piece of this, we know this is a 120-degree sector out of the full 360. And again, we're talking about the area of the circle, not the circumference of the circle. So it's going to be the area of the sector out of 9 pi. 120 over 360 is 1/3. We can cross multiply that. We get 9/3. 9 divided by 3 is 3. The area of the triangle is going to be half the base times the height. Or the altitude. So for this particular triangle, I know this is a 120-degree angle. I also know that it's an isosceles triangle, which means that these are 30 each. And cut this thing in half, and you have two 30, 60, 90 triangles, the hypotenuse of which is 3. So the short side is half of that. So the area of the big triangle, the base of this triangle, each half being 3 root 3 root 3 over 2, becomes a full 3 root 3. So the area of the triangle is going to be half the base times the height. This simplifies to be 9 squared of 3 over 4. If we're going to do this in exact terms, it would be 3 pi minus 9 squared of 3 over 4. And it does say leave your answer in simplest radical forms and in terms of pi, and that's as close as we can get without plugging stuff into the calculator and rounding. 20 is a hard problem until you see it, and then it's fairly simple. If we were to break this in half, I know that we have 3 congruent small circles inside the big semicircle, because the diameter of each of these small circles is 6 centimeters, the radius of the big semicircle, which means that the area of this piece right here is the same as the area of this piece right here. If we were to redraw the shaded area with the piece moved around, it would look like this. So what we're actually looking for is a just creative rearrangement of a quarter of the big circle. The big circle being pi times 12 squared. Or 36 pi. And that is the review. I'm going to leave you to do the proof on your own. I hope you learned something. I'll see you on the test.